people actually watch it? There are.
How many subscribers do you have?
That's subscribers, I don't remember, it's like 6 or 7. The other day, somebody named Vortex Lord subscribed. So, not sure if that was one of you guys or not.
Is it shady?
So, Vortex Lord. Anyway.
It could be your mom.
Yeah.
Probably have like a groupie or something.
Probably. These are so awesome. I can't help but have groupies. They're so awesome. So, yeah.
Have you ever been recording your time even with the test scores?
No, I just started. So, anyway.
Much like Vortex or like comment. Thanks for the shout
Yeah,
out.
I know. Yeah. I don't even know if Vortex Lord is a he. It might be a she. I don't know.
Vortex lady. It's it would be Lady Vortex. Lady
No, Lord is
Lordess. So,
well, we know he could be.
maybe it's like she doesn't want to be prejudiced against because she's a girl, so she's going incognito as Vortex Lord.
We need to figure out. Okay.
So,
Look at their videos. Go creep.
Special shout out to Vortex
Lord.
for planning something.
What's up, Vortex Lord?
Oh yeah, they're probably not.
Anyway. So,
Oh.
yeah, I'm sure Vortex Lord watches every day that I post.
That's
Anyway. All right. What? Cookies are going to show up tomorrow from Vortex Lord.
Flowers?
All right.
It's just like for you.
So, I was hoping more for cookies as opposed to flowers. Mostly
Flowers is for its process.
Yeah, flowers, that would be creepy. The cookies are just delicious, so.
Doesn't matter.
It doesn't matter where cookies come from. So.
The vortex.
Alright, so. Waves. Our last unit dealing with waves, sound, and light follows logically from our units on energy because when we look at what a wave actually is, we define a wave as the motion of a disturbance, but not the motion of matter. And that disturbance transfers energy. Okay? That's what a wave does. It takes energy from one place to another without anything actually carrying it there. Hopefully you'll see some similarities in some of the things that we've talked about previously when we talked about energy transfer, and the ways that energy is transferred, et cetera, et cetera, et cetera. But the idea being that a wave is transferring energy from one place to another. The next one actually is missing a line where it says so for B, waves carry energy, but no matter is moved. Okay? So for C, that big blank space doesn't have lines, it's going to be disturbance. So it's a disturbance is needed to cause a wave. And more specifically, if we're talking about transferring energy from one place to another, what does that disturbance have to do? I heard it. Work. Okay? Work is required to start a wave. Okay? Because that's what work is. Or sorry, that's what the waves are, transfer of energy. So they got to have work in order for there to be energy. Okay? You can see the movement of it, yes. But actually one thing we'll talk about in just a second here is that you can see the disturbance move, but there is no actual movement of matter. Okay? In some cases you can. Sound waves you can't really see, but depending on what kind of medium they move through and how big the wave is, yeah, you can see. Okay. A disturbance can be one thing, or it can be a bunch of different things. Okay, but it has to be that thing that does work, or the thing that causes work on whatever it is we're talking about. Okay. So here, let's take sound waves because those are the kind of waves. Okay? My vocal cords move in my throat. And those vocal cords moving cause a disturbance in the air around my vocal cords. Okay? they move and they run into the air that's in my throat. And then that air runs into the air that's in my mouth. And then that air runs into the air just in front of my mouth. And it just keeps going on and on and on and on until eventually it hits what? More specifically, your eardrum,
How's it
right?
a wave?
Because it's energy. The movement of my vocal cords is being transferred through the air to your eardrum, and it causes your eardrum to do what?
Vibrate.
It causes your eardrum to move. So that ability to change things, the ability to make things different is carried from my vocal cords to your ear. But the important thing here, does anything actually move from my vocal cords to your ear? No, there's no actual movement of matter. We just sort of move it from one thing to the next to the next. The energy or the ability to change things, right? That being the movement, in this case, the kinetic energy of my vocal cords is being transferred through the air, and it's showing up in kinetic energy of your eardrum because they both end up moving. Does that make sense?
Yeah.
Okay. Anthony, go ahead.
For like waves, how come you can't hear the thing distance?
Eventually, so in very similar fashion to the pendulum, right? The pendulum starts with potential, it gets converted into kinetic, but we talked about the idea that it's not all converted into kinetic because of what? Mostly, what's the one thing that prevents all of that potential? Friction, air resistance. And that's the case when that energy is moving through the air. There's some air friction there as those particles move through the air, or as those particles are running into each other, so it actually loses some of that energy along the way. Eventually, if you're too far away, that energy of my vocal cord isn't strong enough, or there isn't enough of it that's transferred to your eardrum to make it vibrate. Okay? Because it gets lost to heat and things like that as it moves through the air and friction is involved and stuff like that. Okay? Does that make sense?
But isn't like your energy not matter? So why would it get lost?
Because it gets turned into other things that aren't perceptible by your eardrum. Mostly heat. You know, that's the biggest thing. Okay? Great, good.
Can't like sound waves move better? Like
No. They can't. Because remember, it's a wave is energy. It's that ability to change stuff. Okay? But as it's being transferred, there is no movement of the matter that transfers it from one place to another. But at the end, it can end
Good
up
morning, pardon the
causing
interruption. I was trying to make sure I hit a period that I had a lot of seniors in attendance. It is nearing the end of third period, so again, teachers, pardon the interruption, if I could have students' attention, specifically seniors, for a few moments. Seniors, if you were a member of the physics program and participating in the physics day at Cedar Point next Tuesday, please be advised that you need to be in attendance the day prior to the field trip to be eligible to go on that trip. Several rumors have circulated regarding cut days, and while I understand traditions for senior activities like that, those of you that are missing school on Tuesday due to the physics trip need to be in class on Monday. If you are absent on Monday and you are truant, you will not be eligible to attend the physics field trip on Tuesday. If you have a parent call in sick for Monday, they need to speak specifically to an administrator. We will not be approving. I don't feel well Monday. You will probably need to be in class on Tuesday then instead of being at Cedar Point to get caught up on any work you missed due to that illness on Monday. Please make sure that you are in attendance all day Monday to go to the trip on Tuesday. Thank you.
Don't they do stuff like that every year?
We already have friends that they like to preserve. Is everyone in Thursdays? Is it?
So, hey, just so you know, we are still recording, so just be careful with what you say. But anyway, let's
Vortex Lord.
Vortex Lord is guys are freezing.
that's right, maybe Vortex Lord is.
Then we all.
So, you know, I'm thinking though, if we probably, you know, if that is the case, our chance at cookies is probably out now.
Sorry.
Because, you know,
what if he's listening to us right now and he's making him
well, it's not on YouTube right now. So
Not right now, but when he's listening to it, he's just like, they want cookies? I got it.
Good.
What if some like freaking
You know, like,
change or like?
officers, it's just like,
Yep.
or like, you have a class.
Right.
So the sound waves that frequent class.
Yes.
No, it's not happening.
Because we
It's a
probably
frequency.
show you that on
It's a
YouTube pretty.
frequency.
There is a combination of frequency, but also the amount, the level or volume of the sound as well.
I thought when you said a wave, it's like
Now,
an actual wave going like that.
there are different kinds of waves. All waves transfer energy, though. That's this applies to all kinds of waves. It could be sound waves, or it could be you just taking a rope and going like this, right? Or it could be light that comes to us from the sun. All of it is transferring energy from one place to another. Okay? Is that good?
Yeah.
This is general about waves, in general. That was two generals in the same sentence, but whatever. Very good. No, because it's a combination not just of the volume, but also of the frequency of the sound that actually hits it. Frequency is the pitch. In sound waves, frequency relates to the pitch. Okay. That is a possibility. If it matches, this is not something we're going to get into.
They had it on Mythbusters. We should watch
But,
this.
go on YouTube, you'll find it.
Mythbusters. They did it.
But it also
I did
it has to do with something called natural frequency or resonant frequency of a material, which we won't get into, but you can cause greater vibrations in certain materials if you match their resonant frequency. So Miriam, it's not just a matter of how loud something is, it's also a matter of do you match the resonant frequency of that material, blah, 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 blah.
Does wave have anything to do with like when you like put your finger around like that glass and feel like
So, are you doing work on the glass?
Yeah.
Yeah.
Do
So
work.
force
So
and
the
movement.
transfer of
Yeah, it's transfer of energy. It is. It's transferring your kinetic energy of your finger, through the glass into sound waves, blah blah blah. All right. So let's talk about some different kinds of waves here. And I'm going to skip something real quick. Come on. Maybe not. Quick.
Now, for like radiation,
Yep.
does energy travel through waves?
Yes, but a different kind of wave. Okay, so that's actually where we're
What was
talking.
wave carries
Energy.
what was the end? What is that?
So we're going to get to that in just a second.
Oh.
Okay. That one relates to some terms that I need to introduce to you. So let's drop down to mechanical waves. Okay. So mechanical wave. Mechanical wave needs a material to travel through, and we refer to that material as the medium through which the wave travels through. A certain kind of waves need to have a medium to travel through, like,
Air.
well, could be air, could be wires. Okay, so I'm talking more.
Conductor.
I'm talking more. No. Kinds of waves that need a medium to travel through. What?
Sound waves.
Like sound waves definitely need a medium to travel through. Ocean waves
Light
need a medium to
waves.
travel
Medium is a show.
through. Light waves do not need a medium to travel through because, right, they get from the sun to us, right?
Radiation.
Okay. There's nothing in between the sun and us.
Radiation doesn't
Between the
need it.
waves. Well, the waves.
Those are radiation waves. They don't need to have anything.
Radiation is light, or a different kind of light. We'll talk about that a little bit more. So, do you ever hear that? There you go. Anyway, sound waves need a medium to travel through. Waves in the ocean need a medium to travel through. Okay? Now, like a tsunami. Okay? If there's like, are we good with like how?
Yeah.
Are we good with how a tsunami happens? First of all,
Earthquake.
okay? There's a big earthquake, usually on the floor of the ocean. And when the floor of the ocean moves, what does it run into? It runs into water. And then that energy, the motion of the ocean floor, is transferred to that water. Then that water, what? Then that water transfers into the next one, then to the next one, then to the next one. That's a wave. So Miriam, that would be an instance when you could see the motion of that energy as it travels through the medium. Okay? A sound wave you just can't because of the nature of the medium that it's traveling through. But do sound waves only travel through gas? Do they only travel through air? No. Sound waves travel through water, right? your ear doesn't perceive them very well, but they still travel through water, right? Will sound waves travel through a solid? Yeah, put your ear against the door. You can hear what's going on inside of the room a lot of times, right? Okay. They will travel through metal as well, and a lot of times it will travel faster through solids and liquids than sound travels through gas. Because why? What's the particles? How close are those particles in a solid or a liquid? A lot closer. Okay? But the idea being, with the mechanical wave, you need something to travel through. Okay? Going back, as far as progress.
You have like those two tin cans and
Yeah.
a little string through it that just goes through.
Sure. Yeah, that's the idea behind it.
Or actually,
That the string is the medium through which that sound is traveling through, and that because those particles are closer together, you don't lose as much in the transfer through the solid as you do through the air. Right? Anthony asked before, why does it get quiet? Well, it's quiet because that energy is converted into heat energy eventually. The idea being, if those things are closer together, it might not happen as much. So, mechanical wave is created when an energy source causes a disturbance, okay, and the energy disturbance is carried through the medium. When it says causes a disturbance, that's a more generic way of saying what? That an energy source does what? Does work, right, on the medium. All right, good there? What? Let's take a look at this picture. Something to keep in mind. Let's say you take a boat, or maybe just a big stick or a bouncy ball or whatever, okay? And if you take it away from the shore at the beach, right? So you're out kind of far. If you sit there, either in an inner tube or in a boat or something like that, and the waves pass by, do you actually go anywhere? A lot of times, what just happens? You just go up, kind of go up and down. You go up and down. Up and down. Okay. Currents are a little different. Okay, but if you're there, like, and it's just a wave, and you're not at the point where those waves are breaking. Okay, you're farther out than that. You'll just kind of go up and down, or up and down, right? Like a buoy or something like that. Okay? Because as a mechanical wave passes, the medium vibrates. Those particles will sort of vibrate. In the case of a water wave, they go up and down, right? But they don't actually go anywhere. In the case of a tsunami, does the water that the ocean floor originally ran into, does it end up going on the shore? No, right? That water stays by the ocean floor. It just passes the energy from one to the other, but the medium doesn't actually go anywhere. The sound waves that you're hearing from my voice, is the air from my throat actually making it to your ear? No, it's not, right? All it does, those air particles sort of vibrate, they run into the next one, but they end up right back where they started. Unless there's some other force going on there or something like that, okay? All right, good there? That's the picture that's like right in the middle of the page, right? It says, how does the motion of the ribbon illustrate the point of the waves are a motion of disturbance, not the motion of matter? If you have this ribbon attached to the string, either on this spring or on this string right here, right? When you shake the string and it moves, right, wave goes through it, where should that ribbon end up? Right back where it started, right? And we'll look at that a little bit more on Thursday when we do some demos dealing with big sticky. It's a good time. What? It's going to be more of kind of a demo as opposed to a lab, but yeah. So, we'll go out in the hallway, we'll find a big space because we need some big space to do it. What? I'm sure you will. Alright, we get on mechanical wave. There are different types of mechanical waves out there. We classify them differently. So, let's flip over to the back side. I'm going to skip those three pictures down the bottom because they just deal with energy transfer and stuff like that. And I'm going to take it to the back talk about types of mechanical waves. The first kind of type of mechanical wave we talk about is called a transverse wave. So that's Roman numeral number 3, types of mechanical waves. Letter A is a transverse wave. If I ask you to draw a wave on your paper, most of you would draw a transverse wave. Okay? A transverse wave is a wave that causes the medium to vibrate at right angles to the motion of the wave. It's pretty long and wordy, but if you think about it, okay? If I take a string and I shake that string, very much like this picture here, this girl in this picture, okay? Your hand is moving side to side, right, or up or down. But which way is that energy being transferred? Away from me, right? Like in a straight line away from me. But Nick, which way is my hand moving? Up and down. Energy is moving straight, the wave is moving straight, but my hand's moving up or down, perpendicular, right? Right angles to the motion of the wave. Is that good? Okay. It can be up or down like this girl on the left, or it can be side to side like this girl on the right. Okay. Say again? Sure. Sure there. I don't know, perhaps Vortex Lord can comment on this video. See what he thinks.
Or she.
See what it is. That's kind of neat, calling it is. I mean, when you're not sure, you're supposed to use the masculine pronoun, right? Like, I don't think so.
What did you say?
I thought it was A.
Yeah, they could comment on that.
That implies there's more than one Vortex Lord, though.
But no, it's like
There's
A.
they.
Out there probably is one
Vortex.
vortex.
It's just, why should be just like a
I
line
know.
like that?
We spent so much time talking about Vortex Lord.
It's just probably so one of
Wait, what is A perpendicular?
So, when we talk about the wave, the disturbance is moving from me to the end of the string, right? So it's moving like horizontally. But the string goes up or down.
Oh, so it's crest beat.
Right. So, no, crest is not B. There's not a place to write down crest. Well, you have to know where the crests are. I'm assuming most of you have heard this before, right? These crests are the top part of the wave, okay? These are important places to identify when we start getting into identifying characteristics of the wave, okay? Then on the other side, you've got your troughs. Troughs are the lowest points of that wave. These places are going to be important for you to identify when we start talking about frequency and wavelength and stuff like that. All right, good there? Transverse wave, cross trough. The other kind of mechanical wave that exists out there is called a longitudinal or a compression wave. And in this case, the motion of the medium is parallel to the direction of the wave movement. So in this case, instead of shaking my hand back and forth, I'm going to push the spring like this. Okay? I'm going to shove it forward and pull it back and shove it forward and pull it back. Right? Is that, in that case, well, I'm doing work on the spring, but now that those particles, right, I'm going to end up with some parts of the spring that are crunched together, and then some parts of the spring that are spread out. Okay? We refer to those crunched together sections as areas of compression, where the particles of the medium are closer together. Okay? And that would be like these two spots in this picture. An example of a compression wave. So, it's nice outside the past couple of days. Some of you probably have your windows open in your bedroom. Right? If you close the door to your bedroom, what happens a lot of time on the other side of your bedroom by your open window? Well, you ever have curtains that sort of like stick to the screen of your window, okay? Or if you have like blinds, sometimes the blinds will move. by slamming the door, closing the door, happens in the garage too. Somebody brought up that, like when the garage door is closed and you like slam the door, you can hear the door, like the garage door shake on the other side of the garage. Okay. Yes, no, maybe. Okay. No. Listen for it next time. Okay. I mean, you can do it with the fridge, although it's kind of hard to hear it because like this would be what was going on inside of the fridge. But you might anyway. When you close the door, right, you're taking some of that air that was in the way of the door and you're smashing it together as the door closes. But as that air gets smashed together, what does it do to the next air?
Makes it smash.
Makes it smash together, right? And then so on down the line, so eventually, right, that smashed up air runs into the curtains, and those curtains move because of it. Remember, a wave is a transfer of energy, an ability to do so. Okay? On the other side, we have something we refer to as, rarefaction. Where compression are areas where the particles are closer together, rarefaction is where they're spread out. In this picture, that would be, come on, computer running slow. Sorry, Vortex Lord. Okay. That would be, now the picture's probably going to change there and there. It also works the same way if you open the door to your room. It also works the same way if you open the door to your room, you can get the curtains to move, but which way do those curtains move now? Instead of being smashed into the screen, right, they come into your room a little bit. Again, transfer of energy. We are done with developing the ring. Alright, so we will pick this up tomorrow.